Hello everyone. Fortunately, I can't be there today. Had some issues. Our nanny had her wedding over the weekend, and then her honeymoon, which she took her honeymoon in Florida, and obviously with the incoming hurricane, she is stuck there, safe, but she is stuck there, and I don't know how long. So tomorrow's my day to stay home, take care of the kids. So. Tomorrow I'm recording this on Sunday, so today for you, so obviously I'm not there, I apologize. So, first period, you have this, it seems like quite a daunting task by looking at it, but after you start looking at the problems, you'll see it's not as bad, even though it still is, quantity-wise, a lot of problems. First period, your goal, as best as possible, is to get all of this done. Okay, this first part right here is basic stuff like if I give you a positive x and a positive y, which quadrant is it in? Similar things to just the coordinate system. Right here, very basics of equations. For instance, find the x and y intercept. So let's say if I give you this equation right here, it says find the x-intercept, you're going to plug 0 in for y. To find the x-intercept, so it'd be x equals 0, or let's make it a little more challenging. Let's do like plus 1. Okay, so if I said find the x-intercept, you plug 0 in for y, or let's make it minus 1. So then you get x equals positive 1, so your x-intercept's 1, 0. If I said find the y-intercept, you plug 0 in for x and solve, so that would look like this, y squared equals 1, and then you solve, you get y squared equals 1, square root, so you get y equals plus or minus 1. That's essentially the types of problems you'll see within there. Anything else within 1.2 here that that I just didn't cover right now, and very basic stuff that you know already, will be covered within the lesson coming up here in the subsequent pages. Now, I apologize if there's any logistical errors with this video. This is Explain Everything program or app that I've used in the past, but it's been updated, so there might be some just logistical issues. I apologize for that. The rest of the lesson will be working on, or the rest of this video will be working on 1.2 and 1.3. For fourth period, you should have predictably all of 1.1 and 1.2 done of Friday, and now we're working on Monday's homework. And hopefully this video won't be any longer, even though I've talked a lot so far, this video won't be any longer than 15-20 minutes, I'm predicting. And therefore you will have time not only tonight, but you'll hopefully, depending on your schedule, but you'll have time in class to get some work done. So that being said, here I go. I'm going to take a leap of hoping that this works well, but I'm going to move on to the next page and continue recording. Okay, so it looks like we're doing okay here. Alright, so this is 1.2 day 2. This is for the second part of the Monday night assignment for period 1, period 4. You know what I'm talking about, right? We've already gotten through this, so if you need to, period 4, you're solid on this, just go ahead and fast forward. Okay, so filling in these notes, if we have y equals x squared, we want to know graphically what is that symmetrical to. So well, let's just look. It's a parabola. Symmetrical means if I take any point, its distance from any point gives us the exact same distance in the opposite direction. A parabola, y equals x squared, that'd be symmetrical to the y-axis. Okay, I think I'm going to have to zoom in here some. There we go. Okay. Therefore, what we see is, if I come back up here, say if I have this point right here, that's negative 2, 4, and positive 2, 4, we see that opposite x values give you the same y value, and when we get to functions, we'll talk more about that, but in this case, we're just looking at it in terms of equations. So far, we know that if a graph is symmetrical to the y-axis, then negative x will return out y just like positive x. Therefore, to determine symmetry to the y-axis algebraically, what we will do is replace x with negative x. Sorry, I don't know if you can see the sidebar where I'm clicking on things or not. I'm thinking no, but in any case, I'll try to get that out of the way. We replace x with negative x, and then simplify it, and if it gives us the exact same equation, that means that x and negative x will give us the same y value, and therefore symmetrical to the y-axis. Okay, so let's look at y squared equals x. Well, if you have y equals x squared as a parabola about the y-axis, then y squared equals x is a parabola about the x-axis. Note, you could check this if you solve for y, you square root, you get y equals plus or minus root x. You know, this top part of the graph, let's see, this top part right here, my orientation's a little off, sorry. This top part is the positive root x and this is the negative root x, so y equals plus or minus root x would give us that. So that's what y squared equals x, and we see that's symmetrical to the x-axis, and very similar to that is symmetrical to the x-axis. And also I apologize for the sloppy handwriting. It's not the easiest to write on this, especially when I'm not used to it. I haven't done it in a while. Therefore, if xy is on the graph, then x negative y is on the graph. Because if we look up here, just the same as before, relative to the x-axis, the y-axis now, if we're relative to the y-axis, or the symmetrical to the x-axis, that means like some point up here is, let's see, 2, 4, or 4, 2. This point down here is 4, negative 2. What negative y values give you the same x value if you think of plugging in y values. Typically think about it as inputs and outputs, but again, we're just dealing with equations. We're not dealing with functions yet. Therefore, to determine symmetry to the x-axis, we replace y with negative y, and if it returns out, you can read in front of you, returns out the same equation, then it's symmetrical to the x-axis. Now, we check symmetry to for x cubed. X cubed function looks like that, and its symmetry, if I start at some point up here, I go that far to the origin, and then go same in the opposite direction. That means it's symmetrical to the origin. So I go ahead and write 0, 0 here, and let's see, algebraically, what's that going to look like? Well, let's see, if I have this point right here, 2 cubed would give us 8, and then negative 2, negative 8. So we see that opposite x values give us opposite y values. Therefore, if I plug in algebraically, negative x values, negative x values give us negative y values. Therefore, and vice versa, if x is on the graph, then negative x, negative y is also on the graph. Therefore, to determine symmetry to the origin, 0, 0, we replace x with negative x and y with negative y, and it will give us an equivalent equation. Okay, so let's look down here. Let's start out by plugging in negative x and see what happens. So if I plug in negative x, first I'm testing with respect to the y-axis. Plug in negative x squared gives us the same. Okay, so therefore it's symmetrical to the y-axis. If I plug in negative y, let's see what happens if I plug in negative y just to be sure, so we get a little practice with it. If I plug in negative y in for there and simplify, we get that. Because two opposites turn positive, you look at this and you look at this. Those are literally not the same equations, therefore it's not symmetrical to the x-axis. If I plugged in negative x and negative y at the same time, they would not give us the same equation. They would give us this one, so therefore this is, therefore he's right, therefore symmetrical to the y-axis. Done. That's all you got to do. Moving on to this one. If I plug negative x in, not going to give us an equivalent equation. It would be negative x cubed y minus 125. That's not the same as what we have in front of us. If I plug in negative y, that's not going to work. It will give us, again, negative x cubed y minus 125. But if I plug in negative x, whoops, sorry about that. Here, let's get rid of that. Where's the erase function? There we go. Okay, so if I plug in negative x cubed, plug in negative y for y minus 125. Okay, cube the negative, that's negative, and then, so we have negative x cubed, and we have negative y, so negative times the negative, as we know, is positive, so it gives us x cubed y minus 125. So when I plug in negative x and negative y, we get the exact same equation as we did originally, and therefore it is symmetrical to the origin, or 0, 0, however you want to write it, doesn't matter. That's it. That's all you got to do for those. Okay, so now we can use symmetry to sketch this. So if I test for symmetry here, plug in negative x, that doesn't work. I plug in negative y, that doesn't work. Symmetry doesn't really work as far as determining or helping sketch the graph. Therefore, we can't really use symmetry to sketch a graph. What we're going to do is an input-output table. And the first value that would give us 0 out, I say, well, I want to get out 0 because this is a root function. So I start out at negative 5. Plug in negative 5, you get 0. 1, 2, 3, 4, 5. Then I say, okay, now I want to get out 1 because that's a perfect square. So I plug in, what would I have to plug in to get out negative 1? That'd be negative 4. The next perfect square, remember, just want to do, so that would be 0, and this would be 1. The next perfect square is 4, and then 9. So to get out 4, what would I have to plug in for x to get out 4? That would be negative 1. And then the last one, what would I do to have to get out 9? You could just think of an equation, x plus 5 equals 9. That would be 4, so I graph those points. I have 1, 2, 3, 4. And then 1, 2, 3, 4, 9. Did I do that right? Oh, whoops, I forgot to square root it. I'm sorry. So negative 1, it'll be square root of 4 is 2. Then as a root function. Okay, 4 plugged in, 4 plus 5 is root 9, which is 3. Ah, that was better. Okay, let's get rid of this right here. There we go. Okay, so negative 4, 1, negative 1, 2, and then 4, 3. 1, 2, 3, 4, 3. Since there's no symmetry for it, we just graph it. We're done. Let's look at this one. This one, if I plug in negative x, not going to give us the same equation. If I plug in negative y, that would work. If I plug in negative x and negative y, that would not work. So this is symmetrical to the x-axis because negative y would return out the same. Let's do an input-output table for this. First, let's go ahead and solve for y squared equals, or how about, let's get a little, you can do it either way here. You could solve for y and then, or, what we can do, since we're not really dealing with a function, we're dealing with an equation, at least we're thinking in the context equation. Let's just pick values for y, 0, 1, 2, 3, and then pick out values for x, find values for x, and solve for x. Okay, plug in 0 for y, I get out 1. Plug in 1, 1 squared plus 1 is 2, 2 squared is 4, plus 1 is 5, and then 3 squared is 9, plus 1 is 10. So I graph 1, 0, I graph 2, 1, whoops, 1, 0, oh boy. Let's move this up. Okay, so 1, 0, 2, 1, 5, 2, 1, 2, 3, 4, 5, 2, and then 10, 3. And then I go, oh, okay, I got my sideways parabola here, and since it's symmetrical to the x-axis, I know I can go like that rather than having to get those points. Okay, that's it. We're not going to see much more of that. Perhaps the section is more of like an introductory. That's all we have for that. Okay, so moving on to the next. Okay, so that's essentially 1.2. You do the best you can with the rest of it. 1.3, all stuff you've seen before. Just moving on further into the section, a couple things we might want to take a look at. That may be a little confusing, maybe just asking questions in a context you haven't seen, but we'll do it. Okay, so slope-intercept form, we know this is, let's go back to black. Alright, so y equals mx plus b. M is your slope. Algebraically, given 2 points, x1, y1, x2, y, or given those 2 points, x1, y1, x2, y2. Difference of the y's divided by difference of the x's. Something you haven't seen before. Graphically, we think of it as our rise, which is the change in y, up or down. Run left or right, change in x's, divide the 2. Y-intercept, b is the y-intercept, where that value is 2x plus 4, the y-intercept is 4. as a point is 0, comma b. Standard form is ax plus by equals c, where a, b, and c are integers. A typically is considered to be positive. I'm fine with it being positive or negative. So for instance, you have something like 2/3 x plus 4 equals 10. That's not an integer, so you gotta multiply by 3, so you get 2x plus 12 equals 30. Okay, there's your standard form right there. And then as far as what all that means, well, standard form has its uses, particularly finding x and y intercepts, really easy using standard form. You can get it in a slope-intercept form. We know, like, solving systems nice to be in standard form. Okay, horizontal lines go through the coordinate x comma a, then the equation is what? Okay, let's see, if I have the xy coordinate system, let's say I have a point here, x comma a, that means right there the y values, that means I go over some x value and I go up a. If you look, any point on here is going to be the same, like if that's the point, x comma a. All points on here are going to be a value, meaning the y value is the same. So it's y equals a in general. Typically, common fallible mistake is that horizontal lines are x equals. They're not x equals. They're y equals. So y equals a. Horizontal lines are y equals a, and vertical lines, therefore, going through the point AY, then are going to be x equals a. Right? Because of the same idea. If I graph a vertical line, say XY coordinate system, vertical line here, let's make it like x equals 4 is used specific example. So I have 4, 0, 4, 1, 4, 2, 4, 3, etc. Vertical lines have same x values, so we just say they're x equals. Parallel lines, slopes are equal, and y-intercepts are different. If they weren't different, they'd be the exact same line. Okay, perpendicular lines have, as you know, opposite reciprocal slopes, and same or different, doesn't matter. They could have the same or different y-intercepts, because if they go through the same y-intercept, but they're perpendicular, they're different lines. They can be perpendicular, but have different y-intercepts. Usually graph different perpendicular lines having the same or different y-intercepts. I've just given an example. Let's say 2/3 is the slope of one line perpendicular to it. The slope is going to be the opposite, so we make opposite and then reciprocal, flip it, I get 3/2. Done. Okay, moving on. Find the slope, y-intercept, and graph of that. So if they want us to find the slope, we have to solve for y. So it's not a big deal. Let's go ahead and solve for y. So I have negative 8y, subtract 3x over. I'm going to put that term first. Get plus 16. Divide by negative 8, so I have y equals 3/8 x minus 2. So I'm just going to say it. Slope is 3/8, y-intercept is negative 2. So then when we graph it, we just go over to negative 2. Graph it and then go up 3, 1, 2, 3. I'll use a pointer. 1, 2, 3. Whoops, I forgot it's not oriented. 1, 2, 3, and then over 8. 1, 2, 3, 4, 6, 7, 8, right there. I think I got the right point. You get the idea. Easy peasy. Alright. Given a line with that, find the equation in standard form. Now, other form that I didn't have earlier is y minus y1 equals mx minus x1. Make sure you write that in your notes. That's point-slope form. Very useful form. Easy way to get slope-intercept when given a point and slope. Now, backing up a step, where does that come from? We know that if we have slope of a line is equal to y2 minus y1 over x2 minus x1, and for fun, we're going to multiply both sides by the denominator. I'm not going to write it on the other side, but written over here, and then moving the y's to the left-hand side, we have y2 minus y1 equals m times x2 minus x1, and then if we generalize, We get rid of that, and we get rid of that. We now have point-slope form. So it's a way of relating one point and a slope to y and x. So let's go ahead and use this. You use slope-intercept form if you want, but I think point-slope is nice. So we have y minus 4, slope of 5, x minus negative 10, so it'd be x plus 10. So I have y minus 4 distribute, we have 5x plus 50, and then that would give us y equals 5x plus 54. Whole time it says find equation in standard form. Well, you can't go straight into standard form. First, if we get this form, now we can get in standard form by moving over the x term. Sorry I'm not using my space really well, but again, I'm just simply not used to this app. I haven't used it in a while, and it has changed. So in any case, I just move over the 5x term to the other side, so it makes it negative 5x. I'm fine with keeping the term negative. That's no big deal. Okay, given a line through those 2 points, now we're just working with slope with a fraction. So y2 is negative 3 minus y1 just makes it a plus 1. 1/3 minus 2, and side note, it can go in any order, provided whatever order you go in for the y's, you go the same order for the x's. Okay, we're going to be doing a lot of this year. This is complex fraction, which is when you have fractions within a fraction. When I say complex fractions, no, complex numbers are imaginary numbers, 8 plus pi, imaginary and real. That's not what I'm talking about. Complex fraction, whenever you hear complex fraction, you think of a fraction within a fraction like this, like 1/3. What we do is we take the LCM of all the smaller denominators, in this case 3, means smaller denominators of the smaller fractions, and multiply the large fraction by that LCD. So now this right here is lining up with the numerator of the large fraction. This lines up with the numerator of the this lines up with the denominator of the large fraction. And now we can distribute that in. When we distribute this into here, we get negative 9, so we get m equals negative 9. When I distribute this into here, I get plus 3. So I'm going back and, oh boy, I don't want that. Going back and forth between different functions in this app, sorry. And then take this one, distribute it in. Now, remember, this is in the numerator. It's like 3 over 1 times 1/3. That will give us 1. We have 1 here, and then negative 2 times 3 is negative 6. And that gives us negative 6 over negative 5, which, oops, sorry about that. Got a little nastiness on the iPad. I was trying to clean it off. Okay, so, smudge or something. Okay, so it's negative 6 over negative 5 is 6 over 5. Now, you may have said, well, Mr. Fossey, coming back to up here, I see 1/3 and 2. Well, I'm just going to get like denominators and then combine those and make that, and then multiply by the reciprocal of, multiply this by the reciprocal of that. You can do that. Overall, though, our goal is in mathematics to be accurate and efficient. When we use this LCD of the smaller fractions and multiply that LCD by the numerator and denominator of the large fraction, you come out with the most efficient method for simplifying that expression. Every single time, there's not one case I've come across in math, a complex fraction like that, where the other way is easier. So I highly suggest you get really good at it. It's not going anywhere. We're going to see that a lot this year. Okay. So now we have a slope and we want to use a point. Which point do we want to use? I think 2, negative 1 is much easier. So let's do that. Y minus negative 1 would be y plus 1 equals 6/5 x minus 2. Distribute in. So I have y plus 1 equals 6/5 x minus 12 over 5. Subtract over 1. I'm going to combine that with the minus 12 over 5. When we subtract 1, get like denominators. That's negative 5 over 5. Combine numerators, negative 7 over 15. Done. Okay, next. Again, I'm trying to get this done in a reasonable amount of time so you can start on the homework. Find the slope in the equational line that goes through that. Find the slope-intercept form. Slope-intercept of the equational line that goes through the point that with the undefined slope. Well, what are undefined slopes? Those are vertical lines. Because that, if I went from one point to that point, that would be going up 4 or going up 2 or however much, but running 0. So if I run 0, I'm sorry, get rid of that. If I run 0, then I have a vertical line. So whenever you see slope undefined, we have a x equals, because it's a vertical line. So what is the x value of the point? X equals -10. You are done. Okay, that is it. So work on that homework from the Friday assignment for period 1. Period 4 you've done already. And then finish up with the rest of 1, 2, and 1, 3. Best as possible. I know it's a lot of problems, so do the best you can with it. And then we'll come back tomorrow and move forward from there.